Hello friends, here we are again. Welcome to chapter 2. We will see in that chapter two important theorems. First, we must say that number 1, formerly, was considered to be a prime, but today, virtually since the early 20th century, mathematicians prefer not to include it and start with number 2. Of course, number 1 meets the rule to be a prime, but its trivial nature leads to its rejection, as it does not actually contribute with anything. In addition, including number 1 as a prime causes troubles in some conclusions and theorems. So, dear friends, number 1 is not a prime. To move forward, we must know one of the most famous theorems of mathematics, and therefore its grandiose name, the Fundamental Theorem of Arithmetic. It is really important, because it shows the special relevance of prime numbers. The Fundamental Theorem of Arithmetic, originally from the Greek Euclid, reads as follows. Any positive whole number greater than 1 is either a prime itself, or it can be decomposed uniquely into a product of prime factors. Euclid of Alexandria was a brilliant Greek mathematician, author of his best-known work, Elements. He lived during the reign of Ptolemy I, centered in the year 300 before Christ. We know very little about his life, basically because of what other biographers wrote much later, like the philosopher Proclus in the 5th century AD. However, his great work is well known, thanks to the translation that the Arabs made of the Greek, and which reached our Middle Ages. Euclid is considered the father of geometry, the Euclidean geometry, which has been taught from its origin to the present day. Elements, his great work, is a compendium of mathematics and geometry, which includes the knowledge of the time, to which Euclid makes a major contribution with his own work, and contributes to mathematics with important aspects of the proof. It is divided into 13 books. The first includes the principles of geometry, which are still used today in everyday life. In Book 7, Proposition 32, Euclid includes his famous theorem, called today the Fundamental Theorem of Arithmetic. Before going on to proving this, let us take a closer look at the significance of this theorem. What it means is that all natural numbers can be built only taking into account prime numbers. It is as if prime numbers were the building blocks of the wall of natural numbers, as if primes were atoms that make up the matter. Only using such atoms in certain proportions we can build any element or material. We could almost say that the only numbers that exist are primes. The others do not exist, because they are nothing but a combination in different proportions of the first. We could imagine a numerical line in which only prime numbers are marked with gaps in the marks corresponding to composite numbers. We can forget about composite numbers. Really, they do not contribute with anything, because deep down they are nothing but well-combined prime numbers. Well, let us not go that far. How to prove the Fundamental Theorem of Arithmetic? We know from evidence that, at least, a few numbers can be expressed as the product of prime factors. 2 is a prime number, so is 3. 4 can be expressed as 2 times 2. 5 is a prime number. 6 can be expressed as 2 times 3. 7 is a prime number. 8 can be expressed as 2 times 2 times 2. 9 can be expressed as 3 times 3, and so on. Let us suppose, for example, we know this up to number 23, Then, the next number, 24, is either a prime or a composite number. If 24 were a prime, it is not. Then we had proved the theorem for number 24. If 24 is a composite number, it is, then 24 must necessarily be the product of at least two numbers different to 1, and which both must be smaller than 24. For example, 24 equal to 3 times 8. But 3 is a prime, we know this, and 8 is a composite number, which we already know that can be decomposed as a product of primes in the form 8 equal to 2 times 2 times 2. So 24 equal to 2 times 2 times 2 times 3. We have proved the theorem for 24, and we can add it to our list. If now we want to prove the theorem for 25, we should repeat the steps, and we would get the result 25 equal to 5 times 5. But what if we would want to prove the theorem for any number, for the infinitely many natural numbers? Well, it is about not committing to any particular number. We will not talk about 23 and 24, but about n and n plus 1. And we will not talk about 2 and 3, but about p and q. Okay, let us suppose that we know how to express as a product of prime factors all numbers up to a number any, which we will call n. Then the next number, which we will call n plus 1, is either a prime number or a composite number. If n plus 1 is a prime, then the theorem is proof for all number n. If it is a composite number, then n plus 1 must necessarily be the product of at least two numbers different to 1, which we will call a and b, and which they must be smaller than n plus 1. That is, n plus 1 is equal to a times b. As up to n we know how to decompose a number in prime factors, we must be able to express a and b this way. A is equal to p sub 1 times p sub 2 times p sub 3 times p sub I. B is equal to q sub 1 times q sub 2 times q sub 3 times q sub j, where p sub 1, p sub 2, etc. are the prime factors of A, whichever. Likewise, q sub 1, q sub 2, etc. are the prime factors of B, also whichever. Therefore, we can write that n plus 1 is equal to A times B, equal to p sub 1 times p sub 2 times p sub 3 times etc. times q sub 1 times q sub 2 times q sub 3 times q sub j. That is, we have been able to express n plus 1 as the product of prime factors. Since we knew from the beginning that it was possible to decompose up to n, and now we know that it is also possible to decompose up to n plus 1, then we will know how to decompose any number, however large. This is the power of mathematics. We are absolutely sure that this is true for the infinitely many natural numbers without having to check it for all them, which moreover is impossible. This method of proof is called proof by induction. For the verification of a property in a particular case, necessarily induces to verification for the following case. In mathematics, there are many proofs by induction. Therefore, now we can safely state that prime numbers are the structure on which all integers are supported. There is just one more aspect of their personality. They are primes, that is, the principal ones. This theorem has a second part. The decomposition into prime numbers is unique, that is, A number cannot be decomposed into two sets of different primes, but only in one, independently of the order of the factors, of course. Let us prove it. Imagine that any number n greater than 1 can be decomposed as a product of prime factors in two different ways, where the p's are a set of prime factors and the q's are another set of different prime factors. If we look at p sub 1, obviously p sub 1 must divide evenly n, so we can write that the last fraction must be an integer, so p sub 1 must divide one of the prime factors q sub 1, q sub 2, q sub 3, etc. Imagine that p sub 1 divides any one of them, which we will call q sub I. Then, since q sub y is a prime and p sub 1 divides it evenly, necessarily q sub I over p sub 1 is equal to 1, so q sub I is equal to p sub 1. If we rename q sub I as q sub 1 and the initial q sub 1 is renamed q sub I, nothing changes, and we conclude that q sub 1 is equal to p sub 1. So, we can write that we repeat the reasoning with q sub 2, and we obtain that q sub 2 is equal to p sub 2. So, we can now write that repeating the process for all the factors, we conclude that every q sub I is equal to every p sub I, and that u is equal to v. So, there is only a possible decomposition into prime factors of a number n. We had started from an assumption, and we have seen that such assumption cannot be verified in any way. So, this assumption must necessarily be false. This step of proof is called proof by contradiction. How many prime numbers are there? There you go. Well, it seems that there are infinitely many, as we can always find a greater prime number. It seems? We are not sure. Actually, we can also think that there may be many, but not infinite. So far, thanks to numerical analysis and very powerful computers, prime number hunters have come to obtain numbers that are truly astronomical, immense. Could it then be that, despite the large amount and size of the primes that have been found, believing that there are infinitely many primes, prime numbers really run out in some remote, still unexplored boundary? These questions were already made long before us by Euclid. We are a little late, but let us see how he solved it. Euclid, who was a wonder of mathematics, developed one of the most beautiful, fast, and elegant proofs that mathematics has ever seen. It is true that the notation that was used in the times of Euclid and the mathematical language were not the same as today. But the principle of the proof that we are going to see is based entirely on that of Euclid. And Euclid said, more than 2000 years ago, that the numbers of prime numbers that exist is infinite. It is such a subtle proof that when you finish seeing it, you may be tempted to say that there is a catch. But there is not, I assure you. It can be found in Proposition 20 of Book 9 of his great work, Elements. Let us see it. The number of primes that exist is infinite. Let us suppose that the number of existing primes is finite. That is, that there is a prime number that we will call p sub n, after which there are no more. We can then write that the set of all prime numbers is... Let us now calculate the product of all these primes, and let us add 1 to it, calling the result m. That is, let us do the following operation. Number m, this is indisputable, is a number greater than 1, and greater than any of the primes of our list p sub 1, p sub 2, p sub 3, etc. Applying the fundamental theorem of arithmetic seen before, we must be able to decompose m into prime factors, forcibly. These prime factors can only be among those in our list, because we drew from the fact that there were no more, correct? However, p sub 1 cannot be a prime factor of m, for if it were so, the division m over p sub 1 would be an integer, and it is not, as the remainder of this division is 1. Neither can p sub 2 be a prime factor of m for the same reason. And that is why any element from our initial list of prime numbers can't be a prime factor of m. If any item on the list can be a prime factor of m, and also, forcibly, m must be decomposed into prime factors, then there are two possibilities. The first is that m is also a prime number, a new prime, which would explain why it does not have any prime factor. But did we not say that there were no more primes than those considered at the start? It appears that we now have a new one, m. The second possibility is that m has prime factors that are not on the initial list p sub 1, p sub 2, p sub 3, etc. I mean that there are other prime numbers, new primes, who are not on the initial list. As only the first possibility can happen, or the second, we must contradict ourselves and conclude that the assumption we made at the start on the number of prime numbers being a maximum of n is false. New ones necessarily appear. Nothing here, nothing there. This is elegance, and anything else is nonsense. The maximum elegance is the brilliant step of adding 1 to the product of the factors to get number m. Understood? Let us see one example. Imagine that the only primes that exist are 5, 7, and 13. We create number m as follows. Note that if we divide number 456 by any of the numbers that we have created it with, 5, 7, and 13, the remainder of the division is always 1, so that no number on the initial list can be a prime factor of m. Number 456, applying the fundamental theorem of arithmetic, has prime factors, for sure. Let us see them. None of the primes taken from the initial list is a factor of 456, and instead 3 new primes have appeared, 2, 3, and 19. As before, we can now expand the list of existing primes to 2, 3, 5, 7, 13, and 19, and recalculate number m, coming back to the conclusion that new primes appear. Always more primes, and so on ad infinitum. Some of you may think that I cheated. Where is the catch? We proved that the assumption we had made is not true, so the truth is the denial of such assumption. Let us notice that proving this, which requires using the fundamental theorem of arithmetic, has been easy. As we already knew this theorem, we have been able to apply it, and this has led us to the conclusion that the existing number of primes is infinite. This proof, again, is based on the mathematical technique of reductio ad absurdum, or proof by contradiction. We draw from an assumption that we consider it to be true, and after our process, we come to a contradiction, or absurd. So, we conclude that this assumption is false. It seems that we have not proven anything, that things have been in the air. But be sure that we have proven everything. This proof is brilliant, like its author, Euclid, not me. So far this chapter arises. We leave for the next chapter interesting arguments that arise after knowing that there are infinite prime numbers. Important questions. And where we will also know curiosities that have been appearing throughout history about prime numbers. Dear viewer, at this point you can ask if I have forgotten the object of this collection of videos, which is the Riemann hypothesis. No, in any way, but to get to it we need patience and know the necessary mathematical history. Everything will come. See you in the next chapter.